Thank you very much for the introduction. This is joint work with Arthur Charguéraud, Jean-Christophe Filliâtre, and Cláudio Lourenço. So, since we are quite enthusiastic OCaml programmers, we want to, or we have this goal that is to provide a new general-purpose programming library for OCaml, kind of a standard library where you can find many common algorithms and data structures such as priority queues, hash tables, and all sorts of classical algorithms such as union find and string processing and so on and so on. Okay, and so now you may ask, do we really need a new standard library or some new OCaml library that is that it has so many intersections with other existing libraries? The idea here is that we want this to be a formally verified and specified library, okay? And why? Because OCaml is used very often as the implementation language for, let's call it, sensible software, such as the Coq proof assistant, the Pharmacy static analyzer framework, Astra, Infer, which has been used for quite a long now inside Facebook, Cubicle, the SMT solver, AlterGo, and so on and so on, okay? And so, as a major step in order to build this verified library, we want to present a new, or the first specification language for OCaml, in the sense that this is a generic specification language for OCaml. So let's take a look at, okay, thank you. So let's take a look at, it's working very well now. Okay, so let's take a look at what can we expect from nowadays OCaml libraries. Okay, so this is quite common interface file, an OCaml interface file, which are written in .ml files, MLI files. And so let's assume this stands for the interface file for a queue, okay? Some kind of priority queue. We define the polymorphic type T, okay, to represent the data structures, and very common functions such as creating a new queue, pushing and popping elements from that queue, okay? And if we are lucky enough, maybe we can get some sort of informal comments that describes how the data structure behaves and what does these functions do, okay? So, for instance, I can say that this is a polymorphic type, okay, this one is easy to guess, I return a new queue, initially empty, and so on, okay? But these are rather informal definitions, this is rather informal specifications, so maybe we can move on from this to something a little bit more formal, and that explicitly says to the programmer, or the programmer is convinced of what these functions really do, okay? And we all know and love separation logic, and why should we use separation logic? Well, since OCaml is an imperative language, it makes sense to talk about mutable state. But yeah, as I said, we know separation logic, we love it, until we need to do something more complicated than the swap function, right? Because here, in this very simple file, I would already have to tell the OCaml programmer that this data structure has a representation predicate, where I say that the pointer to the head of the queue is represented by a sequence, okay? And then I have the traditional separation logic predicate, which is also parameterized by the heap, right? And for instance, I would have to say that for the pop function, I have a well-formed queue because of this representation predicate. The logical model, okay, the one that I introduced here with the mathematical sequence, here stands for L, cannot be empty, right? And so at the end, not only I return the previous top or head of my priority queue, I still remain in possession of a well-formed priority queue, okay? And now, the OCaml programmers in the room are saying that I would never read this, I would never use this, okay? So what we want is to take a step further and provide a simple or a simpler specification language that is also as much expressive as separation logic, in the sense that we can still write good and sound specification for most of our, or for a very representative set of the subset of the OCaml language. And this is where we introduce some Gospel specification. For instance, for the queue data structure, we simply say that we model the data structure via as a mathematical sequence, a polymorphic mathematical sequence. And for instance, the create function is as easy as saying, well, this model here, this logical model, it represents the empty queue. So you get a new data structure where the model is the empty sequence, okay? And when it comes to perform some effect on your data structure, you need to state that you are modifying your data structure, right? Okay, so this is what we do with the modifies clause, okay? For instance, here in the push and the pop function. And when it comes to pre and post conditions, it's actually very easy. It's just the requires here for preconditions, and post conditions are introduced via ensures. For instance, here we say that we are pushing the new element at the beginning of the model, and that we pop elements from the end of the sequence model. Okay, so Gospel stands for Generic OCaml Specification Language, and we want this to be a very expressive specification language in the sense, again, that I can write complete and sound specification for my OCaml functions. But most importantly, it must be understandable by OCaml programmers, which are not mainly proof experts, right? So they are, let's call it like Lambda OCaml programmers, so they still can understand the formal specification that we are providing. It is concise, particularly when compared to separation logic, right? And it's quite important, this is not tied to any particular verification tool, as we see later, okay? You can use it with any tool with any verification tool of your choice. And we also define a formal semantics for our specification language, one that is done via translation to separation logic, okay? So let's take a tour around the most notably or the most interesting features of the Gospel specification language. Let's start with read-only arguments, okay? Let's take the isEmpty function, okay? Very simple function that takes a queue and tests if this is the empty queue, okay? The Gospel specification is as easy as this one, okay? Just a very simple post condition. And when we translate it into separation logic, well, actually, we are using a new kind of read-only or temporary read-only permissions that were introduced by Arthur Charguéraud and François Potier in 2017, okay? What this gets is that we know that we are not modifying the queue, right? We are not modifying our argument, so why would we bother writing a very difficult separation logic predicate, and why would we bother to do that in Gospel? So these temporary read-only permissions can only appear in preconditions, like this one here. They are implicitly returned in post conditions, so again, I still get possession of my data structure after calling isEmpty, okay? I do not lose the right to manipulate the queue. And read and write permissions can be locally turned into read-only permissions. That means you can have a syntactic scope for your read-only permission. And this is actually an extension to classic separation logic. This is not only macro expansion of syntactic sure, okay? This is a real extension to classical separation logic. Now, let's take a look at three variants of the concat operation. The first one, let's imagine that we want to merge Q1 into Q2 and clear Q1. And in this case, when I say clear, is that I say that the model now is empty, but I still want to be able to manipulate Q1 after calling in place concat, okay? So that's why I put both of them in my modifies clause, okay? And so I can still talk about the most recent version of Q1 and Q2 in my post conditions, right? And now let's take a look at what this means in separation logic. So again, we believe it's more easy to, or is easier to read Gospel specification than this OR logic, separation logic triple, okay? Because here I would say that I have two well-formed queues that are separated in memory, okay? And when I return, they are still separated in memory, but I update their logical models, right? And in Gospel, contrary to separation logic, we assume, okay, that arguments are separated in memory, okay? When these are modified, okay? In a moment we'll see how read-only arguments can be aliased, right? But when they are modified, they must be separated. A second variant is now you want to destroy Q1, okay? So after executing in-place destructive concat, you no longer want to be able to manipulate Q1, okay? And for that, we introduced the consumes clause, which means it's an effect on Q1, but you lose the right to talk about Q1 in your post conditions, okay? So you can only talk about the old, that means the previous version of Q1, but you cannot say, for instance, Q1.view in your post conditions, only old Q1.view. And this is the separation logic triple that you get, okay? You can see that now in the post condition, you no longer have a representation predicate for Q1, okay? And finally, the last concat operation is one that you want to preserve both Q1 and Q2, so now you return a new data structure or a new Q. And in this case, this is very, very simple. It's just a post condition, okay, where you say that the new Q or the model of the new Q is just the concatenation of previous models, right? And since there are no modifies or consumes clause here, you know that Q1 and Q2 are read-only arguments. Here you go, okay? So now Q1 and Q2 can be aliased, okay? But the result is a fresh Q, okay? Because it's bad practice in OCaml if you return a non-fresh data structure. So in Gospel, we assume that the result must always be separated from the arguments, okay? Another feature about or that we implemented in Gospel are ghost variables, because ghost code is actually very, very useful when you're doing specification and verification. So we also want to support it here in Gospel, in the Gospel language, okay? We introduce it in brackets, okay? And we must give the type of the argument, because you no longer have it here on your OCaml signature, okay? So in this case, what this function is doing is actually very simple. We take an integer n, and we want to compute the power of 2, okay? The greatest power of 2 that is less or equal to the argument, okay? And since I'm returning k as a ghost result, right? I no longer have to put an existential quantification in my post condition, okay? If I was not returning k, I would have to say there is a k or there exists a k such as r is power 2 to the k and so on and so on, okay? So this is actually very useful if you want to avoid, for instance, existential quantification in post conditions, which can be a pitfall for SMT solvers and automated proofing tools. And when it comes to separation logic, well, ghost variables are just as any other regular variables, okay? So there is no need for a distinction between regular and ghost variables, okay? K is just here, now it's existentially quantified. So now that you are getting the feel of how we work with Gospel, it's kind of natural to presume that there is a generic translation scheme from Gospel into separation logic. And there is one. We provide that in this work. So let's take this very generic example where a data structure is modeled via two fields, let's call it like that, left and right. And let's imagine this very, very generic f function where I manipulate a bunch of these arguments, 4 arguments of type t and another argument of type integer. I return a triple containing 2 Qs or 2 data structures, and I also have a ghost result and another ghost argument. I have my precondition, modifies and consumes, and finally post conditions, okay? And so this is what we get in separation logic, okay? So I do not want you to read all the details, okay? So let's just point to the most important ones. Well, implicitly, all the variables that I need to build my arguments are universally quantified, okay? And now, every one or every data structure or every argument that I know it has some kind of mutable model, okay, here t, and if these parameters do not appear in the modifies or the consumes clause, they are turned into read-only arguments, okay? So this is why P4 here, this one, okay, so it's not neither in modifies or the consumes clause, it's a read-only argument, okay? Implicitly, this one will be returned in my post condition, but again, consumes P3 will imply that I no longer have access to P3 in my post condition, okay? Yeah, and P5 and P6 are the results, so here they are with their representation predicates. Okay, so this is the general translation scheme from gospel into separation logic. This is actually our semantics, right? Other than the language itself, we developed a complete toolchain around gospel, which means that we parse, we type check, and we give means to translate gospel into several verification tools, okay? And to do the parsing part, we actually make a small patch to the OCaml parser itself, one that where we identify these special comments. This is where you put your gospel annotations, and we turn it into these attributes, okay? This is supported by the OCaml compiler nowadays, so it's kind of a special attribute that is turning to, we are turning gospel specification into this attribute. This is sort of the same way that the OCaml parser is treating comments nowadays, okay? They are also turning documentation comments into these special attributes. Okay, yeah, and then we attach the corresponding gospel parts into their corresponding OCaml declarations. And when it comes to type checking, well, it's actually the classic ML type checking and type reference. We also provide a standard library for gospel, one where you can find classical theories about integers, sequences, and sets. There is data structures that are very useful when it comes to write specifications. We also have logical models for built-in OCaml data types, okay? And these are written in regular .mli files, so the compiler can still, or you can still use a regular OCaml compiler to process these .ml files, okay? Our main case study is the vocal library, which stands for Verified OCaml Library. So, as I said in the beginning, our main goal was to build a verified library. So, the first version of vocal, which is publicly available now, already features these 8 fully verified modules, these 8 fully verified data structures and algorithms. And what's most important here is that all of the interface files are specified using gospel. Okay, so this is why we say this is our main case study. And an important aspect about the vocal library and the vocal project is that we want to use we have been using 3 different verification tools in combination with each other, okay? For now, we've been using Y3, COC, and CFML. All of them have their own advantages, okay? So that's why we want to use collaboratively all of these 3 tools. And this is only possible because gospel, again, is not tied to any of them. So we can very well imagine that one day I will add here a new verification tool, okay? One that takes gospel or one where we process the gospel specification and translate it into the input language of the verification tool, okay? So, and what's also important here is that not only we provide verified implementations inside all of these 3 verification tools, we actually have a very important step where we show that the specification we give in the language of these 3 verification tools actually refines the gospel specification that we gave in the first place. Okay, so in the picture, let's start with Y3 and COC because they have very similar workflows. So here is what you write, okay, so your interface file plus the gospel specification. And we have tools to translate gospel into the Y3 language and into the COC input language, right? And at the same time that you write your gospel specification for your data structure and algorithms, you start to verify your implementation inside Y3 or COC, okay? So when you're done, now you can do a refinement proof to show that the specification, the more concrete specification, the implementation specification that you give here is a refinement or that it implies the gospel specification that you gave here, okay? And now if you trust the Y3 and COC extraction mechanism, you actually can extract OCaml implementations. And this OCaml implementation, if everything goes well, these are implementations of the interface file in the sense of the compiler. This means that the compiler says that the interface matches the implementations or the other way around. When it comes to CFML, well, in this case, CFML, it's a bit trickier because it takes existing OCaml code. Okay, so you start with your interface file annotated with gospel and with the implementation itself. Okay, in the first level, you still translate gospel into Concat. Okay, because at the back end, CFML is calling the Concat proof assistant. Okay, and now here, when it comes to the implementation part, you call the characteristic formula generated from CFML, okay? And here, a characteristic formula is an high-order formula that represents all the possible OR triple for a given expression or a given program. It's kind of a high-order formula that is describing the semantics of your program and expression. And now, you need to show, again, as a sort of refinement step or refinement proof, that the generated characteristic formula implies the theorem, okay, or the definition that resulted from the translation from gospel into the Concat input language, right? So this is how we are using these three different verification techniques to build the vocal library and to interact with the gospel language. Okay, so to conclude, what we have done so far, well, we have presented the generic specification language for OCaml, so far for OCaml interfaces, and the word generic here stands for the fact that it's not tied to any particular verification infrastructure. So far, we have covered a fairly representative subset of OCaml, and we have also developed a complete toolchain, okay? Our main case study is the vocal library, one where we are using the toolchain that parses, type checks, and translates gospel annotations into the Y3, Concat, and the CFML tool. And what's actually very nice here, or it's very important, we believe that the main ideas behind gospel can be used to provide specification language to other existing programming language, or maybe to use gospel itself as a means to specify programs written in other existing programming language. And for future work, we want to keep extending gospel, okay, to support other OCaml constructions. And we say that we want to extend gospel to cope with OCaml implementations. For instance, it would be quite nice if we could use gospel to annotate programs with loop invariants, for instance, okay? So far, we are not doing that. We also want to extend the expressivity of the language, for instance, to specify the asymptotic cost of some function. This means like clauses to say, okay, this function runs in O n square, okay, or this is a logarithmic function. And there is also some very interesting work that is being developing to the verification of asymptotic costs inside separation logic. So this would mean that we would have to extend our translation scheme to accommodate these extensions to the language. We want to add more back-end verification tools. For instance, the Viper infrastructure. Viper is kind of an intermediate language that features a form of separation logic, so it kind of makes sense to provide a translation from gospel into the Viper language. We also want to identify an executable subset for gospel to do runtime assertion checking in the very much close to what EACSL is doing these days. Okay, and finally, we think that it could be interesting to use gospel as an ingredient to property-based testing. Okay, there is this QCheck tool that is built in OCaml where you can already provide some invariants to guide the test generator, but we think that maybe it would be interesting to feed gospel into the QCheck, and so that it could read OCaml interface files annotated with gospel and then guide the test generation using the specification that we give in these interface files. So, okay, that's it. Thank you very much for your attention.